Welcome to the course on thermodynamics. This is for biological systems. More specifically, we can call this classical thermodynamics for biological systems. As I will explain later during this module, there is another type of thermodynamics that you can use for analysis of biological systems, which we will not cover in this particular course. The textbook for this course is here. This is Smith, Van Ness and Abbott, Chemical Engineering Thermodynamics, 6th edition. The principles were extensively used for chemical engineering issues earlier, and we will use some of those principles for biological systems and a lot more. This will be your textbook. Nevertheless, the order of topics will not be according to this particular textbook. It will be different, but it will be according to your university syllabus. So you do not have to worry about it being different from your university syllabus. Also, the correspondence between the topics covered in this video and the chapter, the corresponding chapter in the textbook, will be given on the course web page. For example, if you look at this table, I have given you a typical example here. You have a table covering topic and the corresponding chapter in SVA, which stands for Smith, Van Ness and Abbott. Module 2, additional useful thermodynamic functions. The thermodynamic functions H, A and G will be from chapter 6. Concept of chemical potential will be from chapter 10. Equations for a closed system, Maxwell's equations will be from chapter 6. Gibbs-Duhem equation will be from chapter 10. Thermodynamic analysis of processes such as lost work and irreversibility aspects will be from chapter 16. So you can go back to these chapters to read up. I have tried to maintain the same notation as in the textbook for this particular video, but the coverage will be a lot more effective, which will help in easier understanding of the material. There are other books that you can refer to. One of the references that I would recommend is Sandler 1989 Chemical Engineering Thermodynamics, that was published by John Wiley. Additional reading, these are very nice books which would be helpful after you understand a little bit. This would be for approaches, completeness and so on and so forth. A very nice approach is and a very nice development of the subject is given in Denby, which was published way back in 1955. It is called The Principles of Chemical Equilibrium with Applications in Chemistry and Chemical Engineering, published by the Cambridge University Press. And also a very good book is Callan. The title is Thermodynamics and Introduction to Thermostatistics, the 2nd edition by Wiley. Let us also look at the approach that we will use in this course. I personally think it is a lot more effective when we are looking at using thermodynamics to analyze and understand biological systems better. The approach for the most effective use can be explained as follows. We have all learned mathematics, and if you think back to your primary days to see how we really looked at mathematics, how your teachers would have introduced mathematics to you, it would be something like this, a simple process of addition. If you look at 3 apples and you add 4 apples to it, you will have 7 apples. Similarly, if you took 3 coins and added 4 coins to it, you would have 7 coins. Instead of talking about 3 apples separately or 3 coins separately and so on and so forth, if we recognize that this can be abstracted as the number 3 and this can be abstracted as the number 4, the sum would always be equal to 7. We will be approaching or using this particular approach, 3 plus 4 equals 7 in this particular course, which is called an axiomatic approach to thermodynamics, and We will present this first and use some examples to show specific applications to biological systems or processes of biological importance. Let us first review, this is going to be module 1, a review of whatever you know already, and what you know already is through some exposure at the higher secondary level itself. We would have had some chapters in physics or in chemistry relating to thermodynamics, at least the first law of thermodynamics, and definitely a course at the first year engineering level which deals with thermodynamics. What we are going to do in this particular module is to review some of the important concepts that we have learnt so far and what we need as the base to take things further in this particular course on application of classical thermodynamics to biological systems. The first concept that we are going to look at is called the system or the control volume. It is very simple, the concepts are very simple, and once we understand them and apply them, it makes it complete. System or the control volume is nothing but the aspect on which we focus our attention. I will explain this a little further as we go along. Some slight difference between the two: the system could be of any shape and size and could also vary over the time of interest of our particular dealing with that system, whereas a control volume usually is a fixed volume in space. It remains constant over the time of interest. The term surroundings refers to everything else in the universe with which this particular system interacts. For example, we probably know, we are all bioprocess people, biotechnology people, so we probably know what a bioreactor is already. You would have been introduced to what a bioreactor is in probably one of your first courses. Very simply, bioreactor is nothing but a vessel in which bioreactions take place. You can qualify it by saying it is a highly instrumented and a controlled vessel in which the bioreactions take place. We also know that the liquid in the bioreactor is called the broth. While analyzing the bioreactor, okay, let me tell you a little further about the bioreactor. This is the input of air into the system. We know that aerobic organisms require oxygen. The source of oxygen is air, and that is typically provided by bubbling air into sterile air into the bioreactor. This is a temperature measurement, maybe this is pH measurement for appropriate controls. This is a stirrer which keeps the cells in suspension, rotating at a particular RPM, controlled. When we analyze this bioreactor, for certain situations maybe the system could be the bioreactor broth. One of the ways of analysis, a very powerful way of analysis, is to look at material balances. What is material balance? If you recall the course that you did it in, maybe process calculations, bioprocess calculations, or a first equivalent course in the biotechnology program, the material balance is a combination, the relationship between accumulation rate and the input rate, the generation rate, the output rate, and the consumption rate. In other words, input rate plus generation rate minus output rate minus consumption rate equals the accumulation rate. And note that we learnt that this is applicable only over the system for which it is written. As I said, this broth could be the system for the application of let us say this material balance principle to some aspects. Nevertheless, as you will see later when you do your bioprocess course, bioprocess engineering course, we can consider a system consisting of the broth and you take the bubbles away from it conceptually. In other words, the system is going to be the broth without the bubbles in it. This is not a real system, or this is not reality, but conceptually we are considering the broth and removing the bubbles from it. This becomes essential for easy analysis of the system towards calculation of something called the volumetric mass transfer coefficient, or the KLA. Okay. Essentially we write an oxygen balance around that particular system consisting of broth minus the bubbles, and that gives us the KLA. So the choice of system becomes very crucial, and an effective choice of system, as you would know, comes through practice. We also learnt that there are 3 kinds of systems depending on whether there is mass exchange between the system and its surroundings across the system boundaries. That across the system boundaries is very important, please make a note of that, and whether there is energy exchange between the system and its surroundings across the system boundaries. The first kind is called an isolated system, where there is no mass exchange between the system and its environment or and its surroundings across the system boundaries, and also there is no energy exchange between the system and its environment or surroundings across the system boundaries. The second kind of system is called a closed system, where there is no mass exchange between the system and its surroundings, whereas there could be energy exchange between the system and its surroundings. The third is an open system, where there could be mass exchange as well as energy exchange between the system and its surroundings. It is easy to imagine closed systems. You take a closed box with some material in it, and there is no way that the material could escape, whereas you can add heat to it and so on and so forth, that is a closed system. You could very easily imagine an open system, but it is very difficult to imagine an isolated system, very rightly so, because isolated system is just a concept. It is very useful to develop ideas and relations and so on and so forth, as we would see in this course, whereas it is not a reality. The next concept that we would look at, review, is the concept of property. What exactly is a property? Properties are nothing but variables such as pressure, temperature, volume, surface tension, viscosity, enthalpy, and others of the system. It could refer to the system predominantly, of course it could refer to the surroundings also. There could be 2 types of properties, extensive properties and intensive properties. Extensive properties are the properties that are additive. You have more of the substance and you have more value of the property. For example, you take some amount of a substance, you add an equal amount of the substance, the volume of the substance could be 2V if the initial volume was V. Therefore the properties such as volume are additive, mass is additive, internal energy is additive, enthalpy is additive, entropy is additive, and so on. Okay. So the properties of the system that are additive are called extensive properties. Typically the value of such a system property is the sum of the values of the same property of all the constituents of the system. If there are very many different constituents of the system and we add the volume of each constituent, the volume of the system, total system, is the sum of the volumes of all its constituent aspects or constituent parts. In contrast, intensive properties are properties that are not additive. For example, temperature. Assuming that the system is homogeneous, wherever you measure the temperature of that system, the temperature is going to be the same. So such properties are called intensive properties, which do not depend on the amount of substance present, or in other words they are not additive. Some examples are temperature, pressure, chemical composition, surface tension, refractive index, viscosity, and so on. Sometimes we do a trick, okay. We define some pseudo intensive properties for our own needs. We know that volume is an extensive property, whereas specific volume, you divide volume by mass, that becomes an intensive property. If you take a homogeneous system, the volume by mass is the same throughout the system, whereas the volume itself would vary depending on the amount of substance present in that system, okay. And we will also consider them as intensive properties in this particular course. So the value of the intensive properties property could vary within the system under certain conditions too. It is not that it should be the same under all conditions. For example, when the system is not at equilibrium, the value of the property of the intensive property would vary in the system. The next concept that we will review is the state of the system. The state of the system refers to nothing but a set of intensive variables of the system. For example, a system is at a particular pressure, temperature, volume. That set of properties, pressure of some atmospheres or kPa, some temperature in degrees C and so on, is called the state of a system. Next is process. Process is nothing but the path or the locus of the states of the system. For example, when the state changes, the state of the system changes, the set of intensive variables will change. As we have seen earlier, state is nothing but the set of intensive variables. The process is nothing but the path or the locus of states of the system, and typically it goes from an initial state to a final state. There could be many types of processes. We will look at a couple of them which are important. A reversible process, this, as you know, it is not realistic, but it is a very good concept. It is a very good concept which we can use to develop arguments and test our results against. That is what it says here. A reversible process is conceptual and it is used to develop other useful ideas or limiting cases. Reversible process is a process that once completed can be completely reversed to bring the system to its original state, and in doing so it leaves no change in the system or its surroundings. The irreversible process is something that is not reversible, a process that when completed cannot be reversed to bring the system to its original state without causing a change in the system or its surroundings. Okay, note this, a process that when completed cannot be reversed to bring the system to its original state without causing a change in the system or its surroundings. Every part of this is important. There are many other processes such as isothermal process, isobaric process, isochoric process, adiabatic process, and so on and so forth, which you have already learnt about in your previous classes. Next, let us talk of components, concept called components. Any system could be made up of maybe a single substance or multiple substances. If it is made up of a single substance or a single component, then that single component is called a pure substance, or if there are multiple components, the system is called a multi-component system. For example, if you take pure water and you consider that as your system, then pure water is a pure substance and the system is a single component system. If you consider liquid water evaporating into air, that becomes a multi-component system, because you have water evaporating into air. The air contains, as we all know, oxygen, nitrogen, carbon dioxide, water vapor already present there. In addition, you have water vapor going in, and there are other species present in the air, and therefore that becomes a multi-component system. Let us look at phases. The pure component or the multi-components can exist in any phase. What do we mean by phase? The phase could be a solid or a liquid or a gas. and these are the only 3 phases that we will consider in this particular course. There are other phases, the supercritical phase, the plasma phase, which we will not take up as a part of this course. For example, pure water at 1 atmosphere pressure exists as a solid or ice below 0 degrees C, a liquid between 0 and 100 degrees C, and as a gas or a vapor above 100 degrees C. Therefore, the phase of a substance varies with the condition. Typically, a PT diagram, a pressure versus temperature diagram, or a PV diagram, PV, P stands for pressure and V here stands for specific volume, which is volume per unit mass, and we have already seen that volume per unit mass is an intrinsic variable. A PT diagram or a PV diagram provides the relationship between the various phases for a pure substance. Let us look at typical PT diagram first. This is a typical PT diagram for a pure substance, P on the y axis and T on the x axis. In this region, what I mean by the region, the combination of temperature pressure values. In this region of temperatures and pressures, the substance is a solid, which is indicated by S. In this region of temperatures and pressures, the substance, pure substance, is a liquid, and in this region of temperatures and pressures, the pure substance is a vapor. Across this line, the solid becomes a vapor, and we know that process as sublimation, therefore this is called the sublimation curve. Along this line, the solid becomes a liquid, we know that is called fusion, therefore that is called a fusion curve, and along this line, which essentially means along these values of temperatures and pressures, the liquid becomes a vapor, and therefore this is called the vaporization curve. Note this point T, this is called a triple point, because as you note, at this particular point there is coexistence of 3 phases, solid, liquid and vapor. This point is C, the critical point, above which you have what is called a supercritical phase. Above this pressure and above this temperature, you have a supercritical phase here. Next, let us look at a typical PV diagram, a diagram between pressure and specific volume for a pure substance. As earlier, P is given on the y axis, V specific volume on the x axis. In this region of specific volumes and pressures, solid exists. In this region of specific volume and pressure, liquid exists, and in this region of specific volumes and pressures, vapor exists. And unlike the PT diagram, we have regions instead of lines where you have a combination of 2 phases existing. For example, in this region you have a solid liquid combination existing, in this region you have a solid vapor combination existing, and under this curve, in this region under this curve, you have a liquid vapor combination existing. The critical point which we saw earlier is represented by PC VC here on top of this particular curve. The next concept is ideality. We all know PV equals RT. R is the universal gas constant, and you know the value given here 8.314 joules per mole per Kelvin and so on. And we all know what an ideal gas is. An ideal gas is something that does not have interactions between its molecules, and also the volume occupied by the molecules can be considered negligible. Some noble gases actually approximate very well to an ideal gas. In other words, some noble gases follow this PV equals RT equation very well, the combination between pressure, volume, specific volume and temperature very well, whereas the real gases behave differently, and the ideal gas model, which is PV equals RT, is the one to which the real systems approximate under certain limiting conditions. Okay. This you have already seen, the ideal gas equation PV equals RT, the real gases under certain conditions do follow PV equals RT, and that is what you just said. Simple and exact relations can be better established for ideal systems, and these relations can be used as some sort of a standard or a limiting case to which actual behavior can be compared. Ideality is not only for a pure gas, it can be of course envisaged for pure substances such as ideal gases, as well as for mixtures of species or even in a multi component system. We saw what ideality is for a pure gas, or sorry, for an ideal gas, PV equals RT, and for a mixture of gases, ideality comes in when the heat of mixing the various species together, as well as the changes in volume when the various species are mixed together are negligible. Now let us look at the three laws that you would have already studied, the three laws of thermodynamics. The zeroth law first. If the zeroth law states that if two systems, let us say X and Y, are in thermal equilibrium with a third system Z, okay, then they are also in thermal equilibrium with each other. It is a very simple statement, and it is actually a truism. You really cannot go about proving it by other means. To repeat, there are two systems, let us call them X and Y. If they are in thermal equilibrium with each other, with the third system, let us say Z, then they are also in thermal equilibrium with each other. This zeroth law actually provides the basis for temperature measurement, okay, as it is shown here. This is the substance X or the system X, this is the system Y, and they are individually in thermal equilibrium with the Z here, okay. The Z is the thermometer which is used to measure the temperature of X or of Y. If X is in thermal equilibrium with Z and Y is also in thermal equilibrium with Z, then X and Y are in thermal equilibrium with each other. Let us consider the condition that we just said, X in thermal equilibrium with Z and Y in thermal equilibrium with Z, okay, which means that the reading on the thermometer would be the same, and therefore the equality of temperature measured on the basis of thermal equilibrium between the system and the thermometer is the criterion for thermal equilibrium between the two systems, say X and Y. Therefore temperature T can be considered a consequence of the zeroth law of thermodynamics, and it is the one that determines thermal equilibrium. Now let us look at first law. The first law is nothing but the law of conservation of energy. The changes in many forms of energy are essentially equated to one another in the first law. There is nothing more to first law. Typically the changes in the energies of the system parts are equated to each other. For example, the changes in the energies of the system internals are equated to the changes in the energies of the system that cross the system boundaries. This is a system that is indicated by the dotted line here. The energies that cross the system boundaries, these two are coming in and this is going out and so on. The changes in energy inside the system is related to the changes that cross the system boundaries. There are two forms of energies that cross the system boundaries, or the forms of energies that cross the system boundaries are actually divided into two categories, heat and work. Why do we need to divide these into two categories, heat and work? Essentially because heat and work are not completely interconvertible. You cannot convert heat into work completely, and therefore you need to consider them as two separate entities. To understand this a little better, let us slightly jump ahead. Okay, we are going to look at this later, but since this is a review, you have already looked at it, we can jump ahead to understand this a little better. The Clausius statement of the second law is as follows: it is impossible to make a transfer of heat from a heat bath at uniform temperature and obtain an equivalent amount of work without causing a change in the thermodynamic state of some other body. Okay, that is a complete statement of the second law. Let me read it again to get it across a little better. It is impossible to make a transfer of heat from a heat bath at the uniform temperature and obtain an equivalent amount of work without causing a change in the thermodynamic state of some other body. The efficiency of such a process is given by work obtained by heat input, and you would have already seen in the previous classes that can be related to 1 minus the ratio of the surroundings temperature to the system temperature. The efficiency can reach 1 only when the surrounding temperature is 0 Kelvin. If you recall, these temperatures are in Kelvin, okay, and reaching 0 Kelvin is impractical, and therefore it is impossible to completely convert heat into work, and that is the reason we need to consider them as two separate quantities. The useful forms of the first law, for us at least, is to begin with when it is applied to a closed system. For a closed system, when there are negligible changes in other kinds of energies such as potential energies, kinetic energies, surface energies, magnetic energies, and other kinds of energies, then you can relate the change in the internal energy delta U to the heat interaction across the system boundaries and the work interaction across the system boundaries. Delta U equals Q minus W is a useful statement of the first law for us. This delta U is the change that occurs inside the system. Q and W are the energy interactions across the system boundaries. What happens inside is being related to what crosses the system boundaries. For a differential process, we can write the first law as du equals dq minus dw, where these d represent the differentials. Therefore, internal energy U can be considered as a consequence of the first law of thermodynamics. It essentially determines the algebraic sum of the heat and work interactions in a process, or heat and work interactions for a system. We also need to understand what state and path functions are very clearly. You would have learnt that the internal energy is a state function. In other words, its value depends only on the state of the system, irrespective of the path followed to reach that state. For example, if the system is undergoing a process from state 1 to state 2, whether the path of the process is one way or the other way and so on and so forth, as by path we mean the set of intensive variables changing and so on and so forth, whether the path is one or the other, as long as it is a state function, the value of that function depends only on the state of the system. The value of internal energy at state 1 would be the same, and the value of internal energy at state 2 would be the same irrespective of the path taken to reach 2 from 1. Whereas the heat interaction across the system boundary and the work interaction across the system boundary are path functions whose values depend on the path taken during the process. This is a very important concept. In fact, we will be visiting this again and again, and at an appropriate time I will tell you an important aspect of this which helps us significantly in developing relationships in thermodynamics. Now let us look at second law. The second law can be stated in many different ways, and one of the statements is as follows: natural processes can never be completely reversed, is one way of stating it. More formally, the entropy of a system in an adiabatic enclosure can never decrease. It remains constant in a reversible process and it increases in an irreversible process. That is another formal way of stating it. The entropy of the system, as you would know already, is defined as ds equals dq by t in a reversible process. As you know, q is a path function, therefore dq reversible by t is a way of defining entropy ds. Entropy is a state function and an extensive property. State function, it depends only on the state of the system and not on the path taken to reach the system. Extensive property means that more the amount of material there, higher the value of the property. If a system and its surroundings can be considered to be in an adiabatic enclosure, very important, please note this: if the system and its surroundings can be considered to be in an adiabatic enclosure, application of the second law gives us that the entropy of the system of both the system and the surroundings always increases in a real process. Now the universe itself can be taken to be in an adiabatic enclosure because the universe contains everything. Okay, there is nothing beyond the universe, so the whole thing can be considered to be in an adiabatic enclosure, which means there is no heat interaction. For the universe as a whole, the entropy of the universe always increases. You can state this mathematically as the changes in entropy of the system plus the changes in entropy of its surroundings should always be greater than or equal to 0, and if we want to replace this by an equality, we say that the change in entropy of the system, ds of the system and ds of the surroundings, equals d epsilon. D epsilon is the amount of energy that is generated during the process. It is of course 0 for a reversible process, as we know, as we saw earlier in the definition of the reversible process, and positive for a normal or an irreversible process. A natural process occurs in the direction of increasing entropy. We have already seen that if you take the entire universe as a system, the entropy of the system has to increase. As long as we have an expanding universe, the natural process will always happen in the direction of increasing entropy. The water in a waterfall will always fall down and never spontaneously go up, and the entropy provides us with a measure to predict whether the water will flow down, to tell that the water will flow down spontaneously, always flow down spontaneously. Entropy can also be interpreted as a measure of the disorder in the system. It is a concept, order, disorder, order everything nice and packed and so on and so forth, disorder not so packed random, not so ordered. Now let me pose this question to you and let you think for a few minutes before I give you the answer. This course is about application of classical thermodynamics to biological system, and so let us start here right away. The biological cell, as we all know, is highly organized, right? There are many processes taking place in it, but the biological cell itself is highly organized. What I would like you to think about is that, does the biological cell contradict the second law? Take a few minutes and think about it, and I will give you the answer. The answer is it does not. Okay, so far we have not come across something that violates second law. That is because of the following reason. The second law is applicable to a system in an adiabatic enclosure, or if you take the system and surroundings as a whole, which can be considered in an adiabatic enclosure at all times. Therefore, although the entropy of the biological cell decreases as implied in the higher order in a biological system, the overall entropy of the cell and the rest of the universe increases during a cellular process, and therefore the second law is not violated. Entropy S, entropy as indicated by the letter S, denoted by the letter S, can be considered as a consequence of the second law of thermodynamics. It determines which state succeeds the other state. Now let me make a comment that I mentioned in the very beginning of this lecture, that is the relationship, the difference between classical and statistical thermodynamics. For biological systems, classical thermodynamics is useful for the analysis and design of bioprocess related aspects and some biological applications or biological reactions. Essentially, when you can consider something to be in the continuum or continuous and so on and so forth, then you can apply classical thermodynamics principles to come up with useful relationships. Let us look at continuum a little clearer. Continuum is a situation when there are a large number of unitary particles, they could be molecules per unit volume, and the substance under consideration can be considered as a continuous one. If I represent that, or to understand that a little better, if we look at a plot of, let us say, density, a system property, versus the number of molecules in that enclosure, and let us say that we are slowly decreasing the number of molecules in that enclosure, till a certain point there will not be much change in the density, and in this region we can say that continuum exists. After a certain point, because the number of molecules per unit volume have gone down significantly, that if you take a reasonable volume the number of molecules keep on changing, then the density will start fluctuating, and as you go lower and lower the fluctuations will become higher and higher, and this becomes a discrete case, a continuum case and a discrete case. The principles that are developed in this course will be applicable only for the continuum regime. By a rule of thumb in biological systems, if the number of molecules under consideration, say inside a cell or so, if it is more than 100, we can still use the continuum principles, whereas if it goes below 100 we cannot use these principles. For example, in the study of protein-protein interactions, we cannot use the classical thermodynamics principles. This is an example of protein-protein interactions. This slide is from a colleague of mine, Dr. Sanjeev Senapati, from his lab. They were looking at the microtubule assembly disassembly using thermodynamics principles, and they do not use classical thermodynamics principles at all, because the concept of continuum is not valid here. But the methods of statistical thermodynamics can be applied under such cases. This course will limit itself only to the continuum regime, and what we will do in this course is first define important thermodynamic variables that are fundamental enough. We will also look at ways to estimate such variables, and then look at the use of such variables and formulations to predict aspects of importance in biological systems at equilibrium. Therefore, it will be predominantly analysis at equilibrium. In the next class, we will start a second module and look at details.